Okay, we're going to be doing the next section in two parts. It's about enthalpy calculations. The goals are to apply Hess's law and find enthalpy change for a reaction. So this is delta R H naught. A lot of times I leave the R off because most delta H's are just for a reaction. How you draw and interpret energy level diagrams, and use standard molar enthalpies of formation to calculate the enthalpy change for a reaction. These first two parts we'll cover in the first section and this part in the last section. So let's take a look at enthalpy calculations in Hess's law. Hess's law basically says if a reaction is the sum of two or more reactions, the delta H for that reaction is the sum of the delta H's for the two or more reactions. So here's a reaction that is the sum of two or more reactions. In this reaction, if you take H2 gas plus 1/2 O2 gas, you get H2O gas, and the change in enthalpy is minus 241.8 kilojoules. Remember, the negative means it's exothermic, and that heat is a product. Now, this is another reaction, and you'll notice that it looks like the first reaction only backwards, except for one important change. Instead of H2O gas, we have H2O liquid. And of course, this is a reactant, not a product. So here we're taking H2O liquid and we're splitting it apart into H2 gas and 1/2 O2 gas. And the enthalpy change for this reaction is plus 285.8 kilojoules. So this is an endothermic reaction, and heat would be a reactant to make this happen. Now, you can see I've added these two reactions together where by adding them, I keep everything on the reactant side and everything on the product side on the product side. That's how we add these reactions together. When you add them together, if it's a reactant in the beginning reactions, it's a reactant in the total reaction. And if it's a product, or if it's a product in the beginning reactions, it's a product in the end reaction. And then we add the enthalpies. And you can see that when you have positive 285 and minus 241, it's going to add up to a plus 44.0 kilojoules. So here's the complete reaction when we sum it. However, let's look at the sum of the reactions. We have H2 gas making H2 gas. So how much energy change does it take to take H2 gas and make H2 gas? And the answer is none. So we can effectively remove these from the reaction. They don't pose any sort of contribution to the overall energy of the reaction. The same for the 1/2 O2. Those can be removed. So when we remove those things that don't really contribute to the energy change, what we have is this. We have that taking H2O liquid, 1 mole of it, and turning it into H2O gas, 1 mole of it, will take 44 kilojoules of energy. And that's energy that is a reactant to make this happen. So it takes 44.0 kilojoules to boil, if you will, a mole of water. So that's how we use Hess's law. Now, there are some tricks that you need to know in using Hess's law. So here are the tricks of the trade. Number 1, delta H is per mole of reaction. So we just saw this reaction previously. H2 plus 1/2 O2 gives you H2O gas, and the enthalpy change for this reaction is negative 241.8. It gives off 240.18 kilojoules. Okay, now what if I double this reaction? So I make 2 moles of H2, and I double the 1/2 and I get 1 mole of O2, and I double the H2O and I get 2 moles of H2O. So here the proportions are the same. However, I've doubled everything. Well, what's the energy change for this reaction? And the answer is it's double. It's minus 483.6 kilojoules. So that's negative 483.6 kilojoules per 2 mole of H2O, or negative 241.8 kilojoules per 1 mole of H2O. They are the same proportions. So you can double reaction, you can half a reaction, you can triple a reaction, you can do whatever you want, but whatever you do to the coefficients of the reaction, if you double them, you double the enthalpy change. If you triple it, you triple the enthalpy change. If you half it, you half the enthalpy change. Delta H depends on the states. So here, you'll see that these two reactions look very similarly. H2O plus 1/2 O2. but in the top case, turning into H2O gas, in the bottom case, turning into H2O liquid. And look at the changes in enthalpy. They are different because the final states are different. It would be the same if the initial states were different. The enthalpy change would be different. If you reverse a reaction, that is, if you take here this product and make it a reactant, and these reactants and make it a product, you change the sign on the enthalpy change. So here, this is a positive 285.8 kilojoules for the reaction. One more, we can write the enthalpy change as part of the reaction if we so wish. So if we take a look at this reaction up here, the minus 241.8 kilojoules, that's an exothermic reaction and the heat exits the reaction. So that means it's produced and therefore it's a product. Now, if we take a look at this reaction right above, we see that that's plus 285.8 kilojoules. Well, that's 285.8 kilojoules to make the reaction happen. So this heat is a part of the reactants. So if it's a negative value, it's a product. If it's a positive value, it's a reactant. And you might wonder, well, here, that's a negative value and it's a product. Shouldn't it be negative here? And the answer is absolutely not. These values here for negative and positive simply tell me whether it should be a product or a reactant. Not that it's really positive or negative. There is no positive and negative energy in the universe. There is just the direction in which it's flown, and that's totally arbitrary. We like the idea that if you're putting energy into something, you're adding energy, therefore it's a plus. On the other hand, if something is giving off energy, it's losing energy, and so that's a minus. So the sign here is simply a convention. If we put it into the reaction, we use a plus for energy that is produced. Okay, and lastly, delta H's are additive. And we've seen this already before, where you add two reactions together and you get an enthalpy change for the final reaction. So let's take a look at this problem here using Hess's law. Suppose you want to know the enthalpy change for the formation of methane, CH4, from solid graphite and hydrogen gas. So we want to know, what is the enthalpy change for this reaction when you combine carbon plus two hydrogens to make methane? Now, the enthalpy change for this reaction cannot be measured in a laboratory because the reaction is very slow. We can, however, measure enthalpy changes for the combustion of carbon. That's really easy to combust carbon. And we can measure that enthalpy change, and here it is. And here we can measure the enthalpy change for the combustion of hydrogen. Here it is. And we can measure the enthalpy change for the combustion of methane. So the question is, how do we use these three reactions to find the enthalpy change for the formation of methane from its elements? So here, what I'm going to do is I'm going to copy what we want onto this sheet of paper. And we're going to write delta R O, or naught, H naught is equal to what? All right, so here are the three reactions that we get to use. I'm going to move the piece of paper up so that we can focus on these three reactions. And let me show you how you go about doing this. So we want to take these three reactions and put them together in a way such that when they sum together, they give us that reaction. So I'm just going to go with the first reaction. See that I have carbon solid, O2, and CO2. The carbon solid is the same as the carbon solid here. So I'm going to use this reaction just the way it is. And so I'm writing it down just the way it is. And I'm going to describe in detail why I am doing this in just a moment. Okay, you can see I leave the per mole of reaction off in my writing. So the idea here is if I'm going to add this reaction to other reactions to get this one, then I want the carbon solid on the reactant side. And I want one carbon solid. So I'm not going to double this. I'm not going to half it. And I'm not going to reverse it. I like it the way it is. Okay, so here you can see that in this next reaction, I've got H2 plus, this is 1/2 O2 gives you H2O. And you can see here, I need two H2s. And so I'm thinking, you know what? If I need two H2s and this only has one of them, I'm going to double that reaction. So 2 H2 gas plus N2 times 1/2 is 1, gives you H2O liquid. And the change in enthalpy of this reaction is going to be 2 times negative 285.8 kilojoules. Okay, so since I doubled the reaction and I forgot my 2 here, who let me forget the 2? Someone was supposed to tell me. Okay, so I've doubled everything, and let's double check and make sure. 2, that's doubled as a 2, 1/2 doubled as a 1, 1 doubled as a 2, and here I've doubled. Okay, so far I've managed to get my carbon in the reaction, and I've got my 2H2 in the reaction. Okay, so now let's try to bring it home. Now you'll notice that to get this reaction here, we need CH4 as a product. And look at that third reaction. We do have CH4, but it's not a product. So how do I make CH4 a product? I write the reaction in reverse. So I'm going to start with CO2 gas plus 2H2O liquid gives you CH4 gas plus 2O2 gas. And here, this is going to be negative the enthalpy of reaction for the third one. So here, it's going to be negative of minus 180.93, which becomes positive 890.3. I think I said 1890, and that's a mistake, clearly. So plus 890.3 kilojoules. So again, the reason this has become positive is because I've taken this third reaction and I've written it so that the reactants are now the products and the products are now the reactants. And so what that means is we have to change the sign of the delta H. Okay, so now I'm going to put a little line underneath all of this, and here's number 1. This is 2 times number 2, and this is the reverse of number 3. And when we add these all together, let's see what we get. Now, rather than just add them all together and make a mess, here's what I'm going to do. I'm going to look for something on this side and see if I find the same thing on this side. So do you see I have two O2s here? Those two O2s take no energy to make the two O2s down here. And here, do you see the two H2Os liquid here? They take no energy to make the two H2O liquids there. And do you see the CO2 gas here and the CO2 gas here? It takes no energy to take CO2 gas and make CO2 gas there. So when I write down the net result, we basically have carbon solid plus 2H2 gas gives you CH4 gas. And this is the sum of those 3 reactions after we manipulated them a little bit. So when I add these numbers together, I've got minus 393.5 kilojoules. And here, if I multiply this by 2, which I'm going to do in just a moment here, roughly that's 290. Twice is what, 580? So 5, it should be about 570 or 571.6, something like that. So 285.5, oh, clear, 285.8 times 2. And so we get negative 571.6 kilojoules. And here we have plus 890.3 kilojoules. And we add these 3 values together, you can see roughly that These two values will add up to probably a little bit more than that. And so we're going to end up with a negative value. And let's see what we get. 393.5. And that's going to be a negative. Oh, I got to start over. Negative 393. Negative 393.5 minus 571.6 plus 890.3. And we get negative 74.8. So this is the energy change for this reaction. And on your exam, if we asked you to do something like this, I would expect to see you to write out the reactions that you're adding together. I would like to see the energy change for the way you have manipulated that particular reaction. So if you double the reaction, I'd like to see that number. You don't have to show me that multiplication there, but I'd like to see that number. If you reverse the reaction, I'd like to see you reverse the enthalpy change. I'd like to see the little line here have you show it all adding up together and cross out the things that are in common on both sides and then write down what's left over down here. And so this is how you figure out the enthalpy change using Hess's law. And we use some tricks of the trade. One trick of the trade was if you double a reaction, you double the enthalpy. If you write it in reverse, you change the sign on the enthalpy. Heck, you could even change the sign, reverse it, and double it. That may be necessary. So the best way to get good at this is to practice some more of these types of things. All righty then. Put that off to the side. And here we have another Hess's law problem. Let's take a look at it. Enthalpy changes for the following reactions can be determined experimentally. So we can do these in a lab. You react nitrogen with hydrogen, you get ammonia, and the enthalpy change is negative 91.8 kilojoules. You can take ammonia and combust it with oxygen, and you get nitrogen monoxide and H2O, steam, because it's a gas there. And the enthalpy change is minus 206.2 kilojoules. You can take hydrogen gas and react it with oxygen gas and make H2O gas, and the enthalpy change here is minus 241.8 kilojoules. And we want to use these values to determine the enthalpy change for the formation of nitrogen monoxide from the elements. Okay. Now, this is a tough one to do because it's a slow reaction. To do this, it's highly unfavored, so you just can't make it happen, as it were. So let's take a look at making this. So what I'm going to do is I'm going to look at the above, and you can see that I have N2 in this first reaction, and I need N2 in this reaction. Now, I can do this one of two ways. I can say to myself, okay, I'm going to take half of that and make this happen this way. Or I can go ahead and use this and realize that I'm using twice as much nitrogen as I really want to use. And I'm going to go with that route. That way I don't have to finagle this too much. Okay, so I'm going to keep it as N2. So when I get done with this reaction and I add them all up together, I'm going to get N2 gas, not half N2. So let's think ahead. If I get half N2 plus O2, if I get N2 plus O2 gives me 2NO, how would I get the enthalpy for this reaction? And the answer is I would half it. So I'm going to go ahead and use this reaction as given. So I'm going to call this number 1, N2 gas plus 3 H2 gas gives me 2 NH3 gas, and the heat of reaction is equal to negative 91.8 kilojoules. So there's one of them. Now, if we take a look at this reaction, you can see that it has nitrogen monoxide in it. And I want that as a product. Do you see how it's a product here? I like that. But now remember, we have to think ahead. So here I've got double the amount of nitrogen that I need. So I want double the amount of nitrogen monoxide that I'm going to need. So probably not 4NO, but maybe 2NO. So let's have all of this. So I'm going to take 1/2 of reaction 2, which means 2 NH3 gas plus 5/2 O2 gas. And so this is one of the few times when you're allowed to use a fractional coefficient, because we're going to add these all together and it should disappear later. You'll understand later why we use a fractional coefficient here when we talk about enthalpy of formation. Okay, so here we're going to have 2NO gas plus 6 becomes 3 H2O gas. And the enthalpy of this reaction is going to be half of 906.2 kilojoules. So half of that would be a negative 453.1 kilojoules. Okay, so now I will need to continue. It looks to me like I also need a half O2 over here. And I have this reaction here. And this is going to take a little more thinking on my part too, because I already have O2 here. So what am I going to do? Well, this is the way I'm going to think about it. I look at the 3H2 here, and I don't see any other H2 to cancel that, and I don't want that as part of this reaction. So that 3H2 has got to disappear, which means on this side, I have to get 3H2. Well, take a look at this reaction. Can't I triple it and reverse it and get 3H2? You bet. Now, if I have 3H2, what am I going to have for O2? I'm going to have 3 times 1/2 or 3/2 O2. And here, what I'm going to have for H2O? I'm going to have 3 H2O. So I'm tripling this last reaction and reversing it, which means the enthalpy for this reaction is going to be 3 times the opposite of 241. So that's plus 241.8 kilojoules. Okay, so I'm taking the reverse and tripling the third reaction. Now let's add these together and see what we get. So we're going to look for common things on both sides. So I need to raise this a little bit so you can see what I've done here. Remember, this is the goal right here. So can everyone see that I have 3H2O and 3H2O gas? They cancel. If they were different states, they wouldn't cancel. Can we see that we have 3H2 gas here and 3H2 gas here? So they cancel. Here's 2NH3 and here's 2NH3. And here we have 5/2 O2 and 3/2 O2. What can I do with that? Well, this is really 3/2 O2 plus 2/2 O2, because 3/2 and 2/2 is 5/2. So 3/2 cancels with 3/2, and I'm left with 1 O2. So I end up with N2 gas plus O2 gas gives you 2NO gas. And the change in enthalpy is the sum of these numbers here. So roughly speaking, these two numbers add up to about minus 540. And 3 times this is roughly 720. So the answer ends up being approximately 180. So let's go ahead and put that into action and see what we get. So negative 91.8 minus 453.1, and then plus 3 times 241.8. And we get the enthalpy of this reaction is equal to 180.5 kilojoules. But remember, we don't want this reaction, we want half of it. So when we take half of this, we get, for this reaction, it's half of the 180. And so we get 90.25 kilojoules. And there's your answer. Now, let's try it another way, just for fun. So what I'm going to do now is I'm going to go ahead and take these three reactions that we have above, and I'm going to go ahead and make them exactly how I want them to be in the final reaction. So can you see how we have N2 here and 1/2 N2? I'm going to take half of that reaction. So 1/2 N2 gas plus 3/2 H2 gas gives you NH3 gas. So I'm taking each of these coefficients and I'm dividing it by 2. 1 divided by 2 is 1/2. 3 divided by 2 is 3/2. 2 divided by 2 is 1. And for this reaction, we get half of 91.8, which is going to be 45.9, negative 45.9 kilojoules. Okay, now if we take a look at this next reaction, you see the 4NO2, and I only want 1, so I'm going to take everything and divide it by 4. So I'm going to get NH3 gas plus 5/4 O2 gas gives you NO gas. And 6 divided by 4 is the same as 3/2 H2O gas. And the enthalpy of this reaction is going to be this divided by 4. Okay, so what's 906.2 divided by 4? About 200, okay, I get negative 226.6 kilojoules. So I went ahead and rounded that. Maybe I shouldn't have. It's really minus 226.55, but I figure since this has 4 sig figs, this should end up having 4 sig figs. But I'm going to leave that there just in case I need it. All right, so from this last reaction, you can see that this has H2, which I already have, O2, which I already have, and H2O, which I already have. Now, we can look at using this in a number of different ways. The way I'm going to look at it is, well, you know what? I've got H2O here as a gas. I've got H2O as a gas here. I don't want to be adding these together, so I need to reverse this reaction. However, I need 3/2 H2O. So I'm going to multiply everything in here by 3/2 and reverse it. So if I reverse it and multiply this by 3/2, I get 3/2 H2O gas, and I get 3/2 H2 gas, and I get 3/2 times 1/2 is 3/4 O2 gas. And I've got to take that enthalpy of reaction above, I've got to reverse it and multiply by 3/2. So when I reverse it, it becomes positive, and 3/2, 3 times 241.8, and then divided by 2 is positive 362.7 kilojoules. And so let's think about it. Does 1.5 of these seem to be about 362.7? Plus, I take the reverse of it, should be positive. Seems about right. So when I add these three reactions together, let's see what cancels. The NH3s cancel. The H2Os cancel. Here we have 3/2 H2 and 3/2 H2, they cancel. And here we have 5/4 O2 and 3/4 O2. So these are going to cancel, but we're going to have 2/4 O2 left over because only 3 cancel. So when we write the reaction, we see that we have 1/2 N2 gas plus 2/4 or 1/2 O2 gas gives you NO gas. And when we add these values together, let's see what we get. So positive 362.7 minus 226.55 and minus 45.9. We add these together and we get that the enthalpy of reaction is equal to 90.25 kilojoules. And here, since this is only good to the 10th, this is only good to here. So we get the enthalpy of the reaction is 90.3 kilojoules. Okay, now if we compare that to what we got before, let me see, where is that? Here's what we got before. We got 90.25. So we got roughly the same answer, but we had to round a little bit differently. So here are the two answers. This is from my first try, and this is from my second try. And we got roughly the same answers by two similar but different approaches. So there's more than one way to skin this cat. And I never knew why anyone would ever say there's more than one way to skin a cat. Why would you skin a cat? Okay, so there we go. Let me put that off to the side. And let's take a look at enthalpy calculations and energy level diagrams. So what is an energy level diagram? An energy level diagram kind of shows you the relationship between products and reactants so that you can see the energy. And basically, it's writing the reaction out. So this is less stable or high energy. And down here is more stable, less energy. And what you do is you take a reaction that we normally write out horizontally and you write it vertically. So here you can see we have A turning into B can be written as A turning into B, where A is lower than B, and it's now a vertical reaction. And here it might be A turning into B like this, where it's also a vertical reaction. So the arrow is now vertical, and A and B are above the arrow and below the arrow. Endothermic reactions use an arrow up because that means that when you add energy, you're increasing the instability of the reaction or the potential energy. Here, you could actually look at this as potential energy. This is more potential energy and less potential energy. Okay. So when you have an endothermic reaction, you use an arrow going up, which means you would have this. When you turn A into B, B has more potential energy. If you have an exothermic reaction, you use an arrow going down like this over here. So here, this means that B is more stable and has less potential energy. Now the products are always written on the line that the arrow points to. So here, this is what the arrow is pointing to. I call this the head of the arrow, and I call the other side the tail of the arrow. So you always write the products at the head of the arrow, and you always write it on top of the line that the head of the arrow is touching. So here you would write the products. Now you see that this arrow is touching this line, so you write products on top of that line. And the reverse is true for reactants. The reactants are always written at the tail of the line, and it's written on that horizontal bar next to the tail of the line. So that's how you draw an energy level diagram. So if I wanted to show you an energy level diagram for a simple reaction before we had H2O liquid turns into H2O gas, and here the enthalpy of the reaction is equal to plus 44.0 kilojoules. How do we write an energy level diagram for this? So step by step, here's how we do it. This is endothermic. And I know it's endothermic because it's positive. So an endothermic reaction would have an arrow up. So here's my arrow up. There's my first step. Now I'm going to write a bar on the bottom and a bar on the top. Now, in a regular reaction, where does the arrow always point to? The answer is it points to products. So here in this reaction, which is my product, H2O liquid or H2O gas? And the answer is, well, H2O gas. So I'm going to put H2O gas here. So now I'm going to take my H2O liquid, that's the reactant, and I put it at the tail of the arrow. So H2O liquid. Now, the one thing you want to add to this to complete it is you want to put the energy into the reaction. So here's how you do it. You put plus 44.0 kilojoules. Now I'm going to extend these bars like that, and I'm going to draw an arrow going down. So if you do the reverse, if you go from gas to liquid, what's the energy change here? Okay, hopefully you got it. It's negative 44.0 kilojoules because an arrow going down is exothermic, so the value is negative. So here, this is the energy level diagram. I'm covering up this part here for this reaction. But we can add this in too if we want and show you that the reverse reaction is an exothermic reaction with the same amount of energy, but being exiting the program or produced from the reaction, not really a reaction, a physical change. And there we go. So that's how you draw an energy level diagram. They're not all going to be so easy. Let's take a look at a more complicated one. So here we have an enthalpy change for the following reactions can be measured. Methane plus oxygen can react to make CO2 and H2O with an enthalpy change of minus 802.4 kilojoules. This is called methanol. Methanol and oxygen can be mixed to make CO2 and H2O with an energy change of minus 676 kilojoules. And we want to use these values and Hess's law to determine the enthalpy for this reaction. So let me grab another piece of paper here. And this is our goal here. And we want to use these reactions above to reach this goal. So let's take a look at that. Which reaction has CH4 in it? The first or the second reaction? The first reaction. This has CH4 as a reactant. Here CH4 is a reactant. Here I need one, here I need one. I like it. So we're going to use that reaction as is. CH4 gas plus 2 O2 gas gives you CO2 gas plus 2 H2O gas. And the enthalpy of the reaction is minus 802.4 kilojoules. Okay, now here, for the next part, I need O2 in there, but these both have O2 in there. So I'm going to skip the O2 and I'm going to go straight towards that, the methanol. Which one of these reactions has methanol in it? And it's the second one. So I like the idea that there's one methanol here and one methanol here, but I don't like the idea that it's a reactant here and it's a product here. Since I'm trying to make this match this reaction, I'm going to reverse the reaction. So I'm going to write CO2 gas plus 2 H2O gas. And so by reversing it, I'm taking the products of this reaction and writing them as reactants. And I'm going to take the reactants and write them as products. Okay, what do I do to the enthalpy change? Since I am writing the reaction in reverse, I reverse the enthalpy change. So it becomes positive 676 kilojoules. Okay, so can I simply just add these two reactions together and get this one? Well, let's find out. You do see that we want to keep the CH4. That's why I'm circling it. You do see that we want to keep this. That's why I'm circling it. Let's see if everything else cancels out the way we'd like it to. Well, the H2O cancels with the H2O. The CO2 cancels with the CH2. Look at this now, though. I have two O2s and 3/2 O2 over here. Okay, so how does that work out to be? Well, 2/2 O2 is really 4/2 O2, right? So how does 4/2 O2 and 3/2 O2 work out? Well, I can take 3/2 O2 from this and make it 1/2 O2 and cancel that 3/2 O2. So when we add these together, you get CH4 gas plus 1/2 O2 gas gives you CH3OH gas. And indeed, that's what we wanted. Okay, so now what do we do here? We add these two numbers together, and you can see roughly it's going to be negative 125, right? So let me turn on my calculator. And we have 802.4 negative minus or plus 676. And I get that the change in enthalpy is minus 126 kilojoules. And you'll notice I rounded it to the ones because this is only good to the ones and this is good to the 10th. So we round it to the ones, which is less precise. So this is the answer to the enthalpy change for that reaction. So let's write an energy level diagram for this. I'm going to start with this bottom one here. And if I start with this bottom one here, actually, here's how I usually like to start. To write the energy level diagram, I take a look at these numbers here because I want to use all three of these reactions. And I start with the biggest number. So do you see that the biggest number is minus 802.4? It's exothermic, so I'm going to draw an arrow that is negative 802.4 kilojoules long. And I'm going to put a little line at the bottom and a little line at the top. And according to this reaction, the arrow is pointing to the products, which are CO2 gas plus 2H2O gas. Now, does it matter that I write this to the right of the line or to the left of the line? It doesn't. I could even write it right through the line, but I'm not going to. Now, the reactants I write on top. So CH4 gas plus 2O2 gas. So I'm putting down the balanced reaction before I started crossing everything out. So this is that first reaction written here. So now I'm going to try to incorporate one of these other two reactions. And what I'm going to do is I'm going to look for something common to here and the reaction. And what I'm going to do here is I'm going to do this one right here. You see this one? CO2 plus H2O gives you CH3OH. Now the reason I'm going to start with this one is because I see CO2 here and I see CO2 here. So it turns out that this reaction is actually right here. Here's my CO2 and my 2H2O, and I'm going to draw a line that is positive 676. So here's positive 676 kilojoules. Now, why is this line shorter than that line? And the answer is because the length of the line tells you the numerical value. So this is 802 long, this is 676 long. This line is shorter than that. Why does the arrow go up? Because it's endothermic. So I'm going to write my little line here. And you see I have my CO2 and my H2O already on this line down here. So what am I going to put on this line up here? I'm going to put CH3OH gas plus 3/2 O2 gas. Okay, so there is my next reaction added in. Now all I have to do is figure out where does this one go? Well, you can see this one's a negative and it's negative 126. Guess what this distance happens to be? Negative 126 kilojoules. Now, why is this a negative going down? And that's because exothermic reactions are going down. So here you can see this as CH4 plus 2O2 gives you CH3OH plus 3/2 O2. What happens with this 3/2 O2 and this 2O2? Well, they cancel out. So here, this reaction is CH4 gas plus 2O2 gas gives you CH3OH gas plus 3/2 O2 gas, but it's really CH4 gas plus 1/2 O2 gas plus 3/2 O2 gas gives you CH3OH gas plus 3/2 O2 gas. So what I've done is I've taken my two O2s and made it into 4/2 O2. Then I've taken the 4/2 and made it into 3/2 and 1/2. These cancel. And so this indeed is the reaction. CH4 plus 1/2 O2 gives you CH3OH. So even though this doesn't have this reaction written out explicitly, that reaction is implied, and this is the energy level diagram for these three reactions. Okay, so I'm going to put that away. And that was the answer to this problem here. So what you want to do is you want to see if you can add these two reactions up so you get that. Find out if you get the enthalpy change and see if you get the same answer I did. And then see if you can write it into an energy level diagram without looking at my work. If you can do that, then you're ready to try another problem where you don't see the answer. Okay, and if you look in the Q&As, you'll probably see this being done again with a different type of problem. All right, thank you for listening, and part 2 will be coming shortly.